Thanks, Professor Yao, for the introduction, and hello, everyone. I'm Bingqiang from School of Astronautics at Beihang University. Today, I'm glad to share our work on the jet dynamics from bubble bursting at a contaminated surface. So I start from a beer. So when we drink a beer, we can see bubble trains rising to the surface, and then we smell strong flavors. Hello? Okay, so this is facilitated by the bursting of bubbles at the beer surface. Because they emit small droplet aerosols to air, so we can smell the flavors. Here I show the bursting of millimeter bubble. Now, this video shows that the bursting starts from the rupture of a liquid film in the bubble cap. Then the cavity below the liquid surface collapses, and a train of capillary waves propagates towards the bubble bottom. After the flow focusing at the bubble bottom, a liquid jet is ejected upwards, and they break up finally into several jet drops. So this is how the bubble bursting aerosolizes the liquid into droplets to air. So bubble bursting aerosols can transfer the pollutants in liquids to air. It is believed to contribute to the airborne transmission of passengers contaminated water in pandemics. And meanwhile, bubble bursting is the main source of sea spray aerosols, impacting the global environment and the climate. In industry processes, bursting of bubbles in electrolyte emits acid mist and also other pollutants in liquids. This threatens human health and equipment safety. And also among the areas, the dynamic of single bubble bursting is important for understanding and control the associated mass transfer. Usually, large bubbles generate film droplets by film rupture, but small bubbles mainly generate jet drops. Here we focus on the jet drops that's generated by a bubble with a size smaller than capillary length. Many studies focus on the bubble bursting with clean surfaces. In this case, at the surface, only the surface tension matters. So two dimensionless numbers, the Bond number and the Onset number, control the bubble bursting flow. Here, the Bond number compares the gravity effect to substantial effect, and the Onset number compares the viscosity effect to the inertia and the capillary effect. So as we see here, these two determines whether the jet drop can be generated. So usually jet drops are generated at a small Bond number and small odd numbers. The jet dynamics of bubble bursting is of particular interest because it finally breaks up and disperses droplet aerosols into air. And the size and velocity of the jet drop also depends on these two dimensionless numbers. For small bubbles with a Bond number much less than 1, the jet dynamics is mainly determined by Onset number. So basically, with increasing Onset number, the jet drop size first decrease and then increase, and the jet velocity first increase and then decrease, both showing a non-monotic trend with increasing Onset number. Many researchers proposed the scaling laws or relationships for the velocity and the radius of the jet drop, as shown here. So the question is how the Onset number affects jet dynamics. It is directly related to the dynamics of capillary waves during cavity collapse. After a bubble cap rupture, a series of capillary waves propagates along the cavity surface. Among them, the last one. That is also the largest and the most energetic one. We call it dominant wave. And the precursor wave ahead of the dominant wave are smaller, but they propagate faster. At a small Once number, which means small viscosity, the precursor waves, these small waves can propagate to the bubble bottom, and it disturbs the focusing of the dominant waves. But with increasing Once number, the precursor wave is gradually damped by viscosity, and this makes the dominant wave can focus at a smaller scale. The vanishing of precursor waves even yields a singularity of wave crossing. That means the dominant wave can collapse into a single point literally. This is what we call singularity. The simulation also showed a similar trend with increasing Once number of viscosity. Smaller, you can see the smaller, the small capillary waves damps more, making the capillary flow of course at a small scale and yielding a thinner and faster jet. And it reached the most effective wave crossing at Once number about 0.03. For this jet, we call it a singular jet or something. Further increasing Once number inhibits the evolution of the jet and then makes the jet larger and slower until finally kills the jet. So the dynamics of cavity collapse and the jet is a result of interplay between capillary viscosity and the inertia. Actually, the Once number can be expressed as a comparison between the collapse rate of bubble cavity and the dispersion rate of capillary waves. So it evaluates the speed of wave propagation and the speed of wave damping. This is why the Once number controls the jet dynamics. These results, of course, it's all about the bubble bursting with a clean liquid surface, but in practice, gas-liquid interface are always contaminated, more or less. The water body in nature and industry is usually dirty, and the surface is almost contaminated, as you can see here, at the sea surface and the lake surface. For example, the sea surface are always microlayer. We call it sea surface microlayer. This layer can also be formed by OS leaks. This generates an oil-covered interface. Also, due to the biochemical reaction, the biological activities in nature, and the biochemical reaction in industry, the water surface layer can also contains surfactants and macromoleculars, exhibiting surface surfactant. They will generate the surface rheology at the liquid surface. Meanwhile, the bubble surface can be contaminated because they can collect organics during rising and forming a compound bubble. We then wonder that how the contaminated surfaces change the bubble bursting jet dynamics. So we focus on three scenarios. In the first case, the bubble is clean and the liquid surface is covered by a oil layer. And in the second case, the liquid surface is clean, but the bubble is coated with a thin oil layer. In the last case, the air liquid surface is absorbed with a protein layer with surface visco elasticity. So let's look at the first one, bubble bursting at an oil-covered liquid surface. This is our experiments. In the experiments, about 0.7 millimeter, a thin oil layer with a viscosity of 5 to 1,000, and a thickness smaller than the bubble is gently placed at the water surface. The water viscosity is about 1 centistock. And the cavity collapse and the jet jetting process are observed with two high-speed cameras from two cross direction. So we found that even with a highly viscous oil layer, jet drops are still generated. But different from the bubble bursting at a clean surface, we observed a liquid thread after the jet break up. This is a typical feature of the highly viscous liquid pinch-off. This indicates that the jet droplets are covered or coated with oil. We confirmed it by collecting the jet drops with a glass slide. And if you remember this region map, you can note that the high viscosity oils or with a high ounce number cannot be aerosolized by bubble bursting at a pure liquid phase. If you make it as a thin liquid layer at the water surface, at a low viscous surface, it can be aerosolized in this case into the jet drops. So in this case, the bubble surface is initially clean. Then you may wonder how the oil transport to the jet droplets. The oil in our experiments are complete wetting at the water surface, so the oil layer will spontaneously spread to the clean surface, clean cavity surface. So here we show the evolution of the macroscopic oil age, macroscopic age of the spreading oil at the cavity surface. In front of the macroscopic age here, actually there exists a precursor film with a thickness about several nanometers. So you cannot observe it with a camera, but you can evaluate the spread time of this precursor wave. You can find that it is much smaller than the cavity collapse time. So this means that the fast spreading of the oil film during cavity collapse forms the compound jet. We also found that with increasing oil layer thickness and oil viscosity, the jet and the jet drops become smaller and faster. So the next question is that how the oil layer changed the jet dynamics. Can we predict the jet radius and viscosity and velocity? So actually, the same trend was found in the study of bubble bursting at a clean liquid surface. When you change the bulk viscosity, when you increase the bulk viscosity, you can get a faster and smaller jet. This is due to the increasing viscous damping on the capillary wave during cavity collapse. And it can make the capillary flow of courses at the smaller length scale and generating a smaller and a faster jet. This jet dynamics is controlled by ounce number, which can be expressed as a ratio of viscous damping rate to the cavity collapse rate. And in our case, at an oil-covered surface, we also found that the capillary waves are damped more when you increase the oil layer thickness and viscosity. So this indicates that the oil layer increases the viscous damping and modifies the jet dynamics. So the dynamics change by the viscous damping. But so how the viscosity, how this extra viscosity works? Then we need to model the enhanced viscous damping by at the compound surface. So assuming the capillary waves propagates at a compound surface with a thin oil layer, so we can express the viscous dissipation by introducing a surface viscosity. this surface viscosity is related to the oil related to the viscosity of the oil and the thickness of the oil film. So this oil film is at the cavity surface. It is spreaded from the oil layer at the liquid surface. So if we know the thickness of this oil film, we then know the displacement rate. So based on the mass conservation, we can estimate this the thickness of the oil film at the cavity surface. So you can finally get the effective viscous damping rate at a compound surface. Here, the TD2 minus 1. So if we know that TD2 minus 1, in our case, we can define an effective Onnesser number. So if it's substituting it into the scaling laws of the jet radius and velocity for bubble bursting at a clean surface, we find you can find that this equation for bursting at a clean surface with the effective Onnes number we proposed can describe the jet radius and velocity in our experiment. Note that we changed the viscosity by about 100 times, and this data from the experiments with different oil thickness. So the conclusion is that in this case, the spreading oil film introduces the surface viscosity and changes the jet dynamics. And the second case I want to talk about is bursting of oil-coated bubble at a clean liquid surface. So this is our experiments. Basically, they're very similar setup, but we need to generate the oil-coated bubble. How we generate it? We use a coaxial orifice, and we inject air from the inner orifice and inject oil from the outer orifice. If you change the size of the coaxial orifice, you can change the size and the oil fraction of this oil-coated bubble. We use a 2 millimeter radius gas bubble and adjust the oil coatings, adjust the viscosity of the oil coating and the oil volume fraction in the compound bubble. So we also use 2 cameras to capture the bursting process. So for the bursting of a clean bubble at the liquid surface, when the bubble size is about 1 millimeter, it will generate jet drops with the size about 0.1 millimeter, about several sub-millimeter. However, when this bubble is coated with a thin oil layer, we find that we observe the very high-speed jet drop, and it has a very small size, just about several micrometers. It is smaller than the jet drop at clean surface by 2 orders of magnitude. And these drops consist of oil only. This means that the bubbles generate pollutant aerosols more easily after contaminated. So this is a contrast between the collective bubble bursting images of oil-coated bubble and bare bubble. It's clear that many tiny drops are generated for oil-coated bubbles. This small or tiny droplets cannot found in that for clean bubble. So actually, this high speed and ultra thin jet is called a singular jet. It is found to derive from the singularity of the cavity collapse. So after the bubble cap rupture, the capillary waves traveling along the cavity surface sweeps the oil coating towards the bubble bottom, forming an oil blob. And the capillary waves enter the oil-gas interface and collapse at the bottom. You can also see there is a teeny bubble. There is a teeny bubble entrapped. This is the typical feature of singularity. So in order to investigate the capillary waves at a complex cavity surface in detail, we conduct numerical simulations. For the bursting of a bare bubble, the precursor waves, these small waves before the dominant wave, still exists when the dominant wave reaches the bubble bottom. So this disturbs the cavity bottom and makes the dominant wave cannot collapse at a small scale. So fat and slow jet is generated. But when the bubble is covered with oil coating or layer, the precursor waves are effectively damped and the bubble bottom is smooth. This makes the dominant wave Gaussian at infinite scale, literally, and yields a singular jet. So precursor waves are dissipated preferentially at the water-oil-gas interface. This makes the singularity of the dominant wave collapse happens. Here we summarize the parameter space for the occurrence of singular jet. We conduct experiments with different oil viscosity and oil fraction, and we define the singular jet as to the jet that with a size is smaller than about 0.02 times the bubble radius. And you can see that the singular jet happens at a very wide parameter range. Note here we use log coordinates. So the singular jet happens at for the oil with viscosity from 2 to 10 centistorg, and when the oil fraction is larger than 1%, you can generate this singular jet. And we also note that if you consider the dimensionless numbers defined with the property with water or oil, the space of On's number for singular jet for singularity of oil-coated bubble is much wider than that of bare bubble. This means the singular jet occurs more easily for contaminated bubbles. So, similar to what we did for bubble bursting at oil-covered surface, we again modeled the viscous damping of capillary waves at water, oil, air compound interface. But in this case, the oil layer thickness is larger than the previous case. So we need to serve the flows within the oil and the water phases, both numerically. So we find that we know that at a clean surface, the damping rate of capillary waves follows this equation, and the damping rate ratio of the precursor wave and the dominant wave is set already, because we know the wavelengths of this of the dominant wave and the precursor wave. But at a compound interface, this ratio of damping rates changes with oil layer thickness, you can see here. And the wavelength of precursor wave also decreases when it enters the oil phase, because the oil have a small substantiation to keep the wave velocity. It must decrease its wavelength. So this makes the ratio of damping rate between the dominant and the precursor waves increase by 10 times compared to that at a clean surface. So this means indeed the precursor waves are more easily damped for a compound bubble. So since we can calculate the damping rate of the secondary wave numerically, we can define a revised On's number here. It compares the damping rate of the secondary wave and the collapse rate of the cavity. So the oil layer does not change the collapse time, but it changes the damping rate of secondary wave. So you can see the line of On's number equals to 11, where describe the lower boundary of singular regime, and the upper boundary is set by the oil viscosity, because high enough viscosity significantly damp the jet evolution. So based on this, based on the knowledge of clean bubble bursting, the jet drops are not considered to contribute significantly to C-spray aerosol in global model, because they are considered to be much larger than the film droplets, and larger, usually larger than micrometer. So, but our study shows that the widely present contaminated bubbles can generate micro jet drops. So this means the rural jet drops need to be considered in future models for the global model C-spray aerosols. The last case I want to talk about is bubble bursting at a viscoelastic surface. Here I show two videos of the bursting two bubbles with the same size, and their bond number and On's number almost the same. But it's clear that there is jet drops generated in the left one, but the jet drops are disappeared in the right one. So what's the difference? So the difference is that we only ate very little proteins in the right case. So the concentration is only 50 parts per million. Why such a small addition make a significant difference on the jet dynamics? This is caused by the surface viscosity introduced by the adsorbed protein layer. So here is our experiments. The surface dilatation elasticity, or the interfacial elastocapillary number, surface stress, and the surface traction. So you can so how the surface elasticity change the dynamic of wave jet. So first, the surface dilatation elasticity dissipates the precursor waves. You can see more and more smooth bubble bottom at a higher protein concentration. This actually helps for the occurrence of singularity. On the other hand, the tangential traction generated dilatation elasticity lower down the dominant wave, because this force drags the capillary wave, right? And this makes a X-shaped bubble tip. You have a neck here, and the neck finally pinch off, and it entraps a small bubble finally. So after this bubble, small bubble formed, the jet, cavity surface reverses. So this process, the formation of jet, the process of jet formation is during this process, the surface expands. So the surface elasticity inhibits this process. So kills the jet and jet drops. So if we replot the regime map regarding to the elastocapillary number EC, we find that EC indeed determines the occurrence of bubble entrainment phenomena. So this also holds when adding a small molecular surfactant twin 80 into the protein solution to adjust the degree of surface elasticity. And this means that the competition between surface tension and the surface elastic. When the surface elasticity effect overweights the capillary effect or larger than 1, bubble entrainment can happen. To conclude, our findings on the jet dynamics of bubble bursting at a contaminated surface shows that a complex interface can remarkably modify the interfacial flow by introducing multiple physical-chemical properties, by introducing surface rheology, or introducing multiple time and length scales, or introducing flows at small scale, coupled with the global fluid dynamics, and thus reshapes the momentum or mass or heat transfer across the interfaces. Okay, so thanks everyone, and I would like to take any questions from you.
Yes, thank you very much. Professor Ji give us a very, very good work. Yeah, I'm thinking, yes, your work actually is very fundamental actually. Because you know why? Because at the beginning, I have some questions in my mind, but after I read your presentation later, and the previous questions actually is solved. So this is very interesting. Yeah. Okay.
Thank you.
Yeah, and you know, there's some text actually on their screen on the windows, and so some of them are actually from mine. Just now I already told you, yes. At the beginning I have some questions, but after I read the presentation later, the question actually be solved. And for example, I asked the question is that do you consider simulation? Actually, you already do some simulations. And regarding the simulation, do you using the safety methods to consider the bubble, the flows or jet here?
Yes. So in this case, for the oil-coated bubble bursting, we conducted experiments. Conducted simulation. This simulation actually is conducted by Professor Jesse Ort at Brown University. So we use basilisk here. It's a open source CFD code, and
using the DNS methods or other methods.
DNS.
Okay, and I also consider you using molecular methods to simulation the bubbles shape in your later presentations. Yeah.
Yeah. No. We didn't conduct molecular simulation, but this is a very good suggestion. Want to know the spreading of the precursor film of the oil, or transport of surfactant moleculars. But we didn't do molecular simulation. We just evaluate the time scale.
Oh, time scale. Okay. Because you do this work very carefully and very detailed. So I'm thinking a lot of information from your phenomenon observed provide a lot of information for us, and we can do it. You mean? I mean that by simulation and to know details of this, what happens and what the working mechanisms, and a lot of theory, and can get it from it. And I have the questions about because you mentioned many times about the clean water. Actually, I don't know what it means. Later, I find your presentation have a bubble. Actually, is opposite to clean bubble.
Yes. So for clean bubble, it means no extra molecules or no extra phases at the liquid gas interface.
Because I'm not working in this area, so I'm not very familiar with this. So I'm so for the clean bubbles and for the contaminated bubbles, it is possible to provide iterative indicator to describe the properties, because you know the property, the content of these bubbles is different. Then maybe it will affect the bubble's shape or bubble's moving or bubble's behavior. This is my wondering question. Yeah.
Mm. So when you have oil coating here, the bubble shape may change initially, actually. So in this case,
what kind of oil?
silicon oil.
A silicon oil. Do you have some physical properties of it? Because about the density, about this, you know, some
density of silicon oil is just a little smaller than water. It's about 930 or 970, like that.
Okay. Yes.
The viscosity is about viscosity here.
Okay. So some question actually the pull from Ping'an. His question is that the bubble is released at the bottom and rise up to approach the free surface. I'm wondering whether the bubble velocity influence the bursting dynamics.
Yes, sometimes it will, but here we consider the bursting of a static bubble. So that means before bursting, the flow field is static. So to achieve this, you need to use a very shallow liquid in the experiments to make the rising distance small enough, and so it approaches the liquid surface with a small velocity, and then it in most cases bursting after it rests there. It becomes still at there. But some cases actually you can find that the bubble oscillates and bursting. So we just neglect this data. So we just study the bursting of a static bubble, of the stir bubble.
Okay, Ping'an, are you all right for his question, for his answer? Ping'an?
Thank you for the explanation. Yeah, because initially I was wondering, the bubble will burst once it touches the free surface. However, now I can understand that you have a very intricate control over the motion of the bubbles, so that to ensure that so probably in your experiment you can hold the bubble to stay for some period along the surface, right? And then you just use a needle to induce the collapse of the bubble, so that you can ensure a very good control over the flow field around the bubble before it bursts.
So in the case of clean bubble or the oil-coated bubble, the lifetime of the bubble is short. So for example, maybe just within 1 second or several seconds. So you don't need to punch it with a needle. But you're right. If there is surfactant, or especially you have BSA, the lifetime of the bubble is very long. And maybe just it can be like several hours or 10 minutes. So you need to punch it, use a needle, or you need to wait a very long time. You don't know when it will burst. And also you cannot control the aging time, because the aging time changes the physicochemical properties of the surface.
Yeah. So very interesting work. Thank you.
Okay, and Professor Zhu has another question here. In the study of oil-coated bubble, numerical simulation shows that the oil is dividing on the water-air interface. Is this always true?
No, it's not dividing. This is, you mean this case?
Yes,
yes.
Yes.
The oil is swept by the capillary wave, right?
Yes.
The oil complete sweating. If you calculate consider the interfacial tension between the for the three interfaces. So you still have a very thin oil there.
Oh, I see.
Everything you cannot see it, but the collection the oils at the bottom is because of the capillary wave, because the capillary wave sweeps the oil coatings here. You can see from the experiment videos.
Yeah.
It's
swept
by the capillary waves. Mm-hmm. So the oils, so the oil layer thickness is thicker and thicker when the with the propagation of the capillary waves. Mm-hmm.
Yeah, so very beautiful video here. So
okay, thanks a lot for Professor Ji's excellent presentation. Thank you very much.
Thank you.
And,
Thank you for the question.